All right, for my next trick, we'll talk about electric currents. Right, so if we have a wire, let's get silver, like this, and we put a voltage on either side, if we put a potential difference here, so this will be V low, this will be V high. A current is going to flow along in this direction. So it's going to flow, the current is going to flow through here just like through a pipe. So these lines here are called the electric field. They're the same electric field as we had before, and they flow directly through the pipe because the current has to stay inside of it. All right. So basically, when this thing has free charges, it pushes everything towards the center. There are some exceptions to that. We'll look at those exceptions maybe a little bit in the magnetism part. So we've got the current flowing this way. That looks good. And we want to figure out what that current is. So basically what the current is in a wire is little electrons following their path. Actually, they're going this way. Electrons going that way. You could do this in a fluid, so you could have ions in a fluid. That would also work, in which case you have positive ions going that way. In that case, it would be through a real pipe, right? It wouldn't be through a wire. So the wire acts like a pipe for electrons, but a pipe acts like a pipe for both positive and negatively charged ions, which will go in opposite directions. So the point there is that the current is the flow of the electrons through here, so through some particular surface here. So take that. All right. So that's part one today, which is the current. Is the flow. From a high potential to a low potential, or of charged particles from a high potential to a low potential. Or vice versa, depending on the sign of the charge, all right? So that's what it is. So we have this area here that it's going through. What that means is the current, which is we call I, and hopefully that's for some linguistic reason, like it's German or something like that. I don't know why it's I. I have to figure that out. Is the amount of charge that goes through this area. So charges that are just sitting there, like in protons, right? Those charges don't count, only the electrons that are moving through over a particular time. And so this amount of charge is going to increase the larger you have that time there. So we'll look at it that way. Let's see. The current is defined to go this way. That is, it's going from the high potential to the low potential. Okay, so that's what the positive direction of the current is. This is the negative direction of the current. Now, because these electrons are negatively charged particles, we count the flow as going this way. So we're looking at the flow of positive charge, and that's negative the flow of the negative charge. So you'd have this for the positive charge, right? Positive charges are going this way. So that's I is that way for positive. And for negative, oops, you have the charge going the opposite direction, but I is still to your right. Sorry, again, screen's reversed. So that's the basic idea there. There are a couple of other things we can look at for the charges. All right, so if you have charge in a wire, then the current will be the motion of electrons. And in that case, you have I is equal to the rate or the number of electrons going through this little surface here times the charge of the electron, which is minus E. Right? So that'll do that. So this is the rate of the electrons. It's not backwards, it was upside down. Okay, so that's one way to look at it, or that's a second way to look at it, and the third way is going to be current in a wire is the free charge, or comes from the free charge. I've erased, this was, oh, I don't have any more room. And that's going to be lambda, which remember is the charge density, the linear charge density, times the drift speed of the electrons. And the drift speed is the speed at which the electron moves through the material on average, including all of the collisions that the electron makes with the atoms in the wire. So there are a lot of these atoms, there are a lot of atoms in the wire. A lot of those are missing electrons, right? So they're little positive charge centers, and the electrons will move through and they'll get deflected by those. So it's like a pachinko machine or something like that. The electrons are moving around in some random fashion, and they accelerate really quickly. We did a problem previously that said if we have 5 centimeters worth of distance for these electrons, they're going to accelerate really, really fast, right? And we don't like that. So they're going to go to, the speed of light sort of speeds. And in fact, that's about the speed of an electron between the collisions. The electron is going to speed up to something like 3/10 of the speed of light in between all those collisions. But there are so many of those collisions in a wire, in a metal, in a conductor, that speed is very, very slow. It's something like 10 millimeters per second. It's very slow, the speed of the electrons going through that wire. So that's that drift speed, the speed that is actually moving through, the progress the electrons are actually making, not just the speed that they're moving between collisions. All right? So I'll do one example of that. I'll probably look at an example that has to do with the line charge, because I love those. And then we'll go through and we'll talk a little bit more about currents in the next videos. All right? Bye now.